Iason Papaioannou, and I work at the Technical University of Munich in the Engineering Risk Analysis group. I work with Professor Daniel Straub. And my topic today of my presentation is on sequential sampling approaches for reliability assessment. So this is kind of a category of methods where we perform sampling in a sequence of steps, where we start from sampling from the original distribution of the random variables and try to find samples from a somehow optimal distribution for important sampling. Before I go and discuss the details on the method, and because I am the first speaker, I thought I should spend some time to define the problem, so what we're trying to solve today. Maybe then the next speakers don't have to say that much on these general things. So why are we sitting here today? So we are civil engineers or mechanical engineers, and we are usually dealing with systems whose failure is associated with high consequences. So these type of systems, examples of which I have on the slide, their failure should be associated, because of the fact that this failure can have high consequences, they should be associated with small probabilities of occurrence. So when designing or assessing such systems, we need to be able to estimate probabilities of failure that range from 10 to the power of -5 to 10 to the power of -8. Okay. However, typically we don't have any data on these rare event regimes. So what we need to do is to somehow extrapolate in order to evaluate this probability. And how do we do this? We do it through using numerical models of the systems we want to assess. These models range from simple analytical expressions to highly complex numerical models that could be, for example, nonlinear finite element models that might need significant computational time to run. And what we do is that we model all the input parameters, including, for example, also model errors, model all these parameters as random variables, and then propagate them through this numerical model. And through this propagation, we can evaluate or estimate the probability of failure of a system. So this seminar, we're looking at high-dimensional problems, so problems based on the abstract of the workshop with dimensions more than 20. I was trying to think, what are these type of high-dimensional problems? So which cases do we actually deal, or do we need to deal with such high-dimensional problems? I have some examples here. Of course, there might be more examples than these. We can have systems, either structural, infrastructure system with large numbers of components. In such cases, we might end up with thousands of components, thousands of random variables. And also in cases where our input includes spatial or time variability. In such cases, we are dealing with random functions. And these random functions have to be discretized to a finite number of random variables. And this number can potentially be very, very high. So examples here are discretization of a random process or a random field through a large number of random variables. Okay, so this is kind of a motivation, the reason why we're here today. So let's try and define the basics. In my presentation, I will model all these random variables through a vector x that is described probabilistically by its joint probability density function f of x. The failure condition of the system is defined through a limited state function g of x, such that negative values or non-positive values of this function denote failure of the system. What we need to do is we need to integrate the joint probability density function of these random variables at the space defined by non-negative values of the limit state function, which is our failure domain. So in principle, what we need to do is integrate this function at the failure domain defined by non-negative values of a limit state function. This is how we can evaluate the probability of failure. There are several ways to go and evaluate this probability of failure. I believe that one of the most, let's say, robust ways to go is to apply simulation methods. Of course, I don't want to say that approximation methods are not good enough. So we know, and we have been using first order, second order reliability method for many years. We know that it can be, they give pretty accurate results in many engineering applications. However, simulation approaches are kind of, they have the advantage of simplicity. They only require to generate samples from the input random variable space, and for each of these samples, just evaluate the system output. So in this case, the limit state function value, and then through samples of the limit state function value, just perform statistical analysis of these samples. So this means that they are pretty robust. They can deal with any complex numerical model. They don't need to evaluate derivatives, as for example, first order reliability method requires. And in the standard, let's say, method for simulation, which is the Monte Carlo method, we have this very nice property that the efficiency of this method actually does not depend on the number of random variables of our system. This makes this type of methods particularly useful for dealing with such high-dimensional problems. When we try to apply Monte Carlo simulation to evaluate the probability of failure, the method is very, very simple. What you need to do is sample the distribution of the random variables, count the samples that fall in the failure domain, and just divide by the total number of samples. And then you get an estimate of the failure probability. What you can already see here is that for this typical engineering example, R minus S, resistance minus loading, limit state function, I have generated 1,000 samples and only 2 fell in the failure domain. So I basically threw away 998 samples. So this kind of makes us understand that the standard Monte Carlo method is not a very good method for evaluating small failure probabilities. And this we can understand a little bit better if we look at the Monte Carlo method more closely. So the probability of failure, which is this integral here, can be expressed as the integral of the indicator function, indicating failure, multiplied by the joint PDF of the random variables, and this actually equals the expectation of the indicator function. The standard Monte Carlo method evaluates this expectation through a sample mean. So it approximates it by taking the sample mean of the values of the indicator function for a number of samples ns. This, of course, in the end ends up to be number of failed samples over total number of samples. One can evaluate the coefficient of variation of the estimate, and you see that this coefficient of variation is inversely proportional, of course, to the number of samples, but also to the failure probability. Okay? This means that this coefficient of variation, in order to keep this number low, for very small failure probabilities, we need to use a very large number of samples. Okay. An interesting thing to point out here is that actually the dimension of the random variable space does not enter the coefficient of variation of the probability of failure. So actually, this coefficient of variation is the same for any basically problem with at any dimension with the same failure probability. Okay, so how can we move on outside standard Monte Carlo method? How can we get this coefficient of variation better? We can apply some variance reduction technique, some technique that tries to decrease the variance of this standard Monte Carlo estimate. And the standard technique to do this is important sampling. Important sampling, what we do is we take this integral and divide it and multiply it with a function which is a density, and it's called important sampling function or important sample density. Then this probability of failure can also be written as the expectation in terms of this new important sampling function of the indicator function multiplied by a weight function which equals the ratio of the density of the random variables divided by the importance sampling function. Then what we can do is that we can sample this importance sampling function and then estimate the probability of failure by taking the sample mean of this expression here. The variance of the estimate of the probability of failure is given by this expression here. Depending on the choice of the importance sampling function, this variance can become significantly smaller than the one that we saw before with the Monte Carlo method. In particular, there is one choice of the importance sampling function where if we plug it in inside this expression, we get a variance of 0. This means that if we are able to sample one sample from this optimal importance sampling function, we will get the exact value of the probability of failure. This is how this importance sampling function looks like. So for a standard normal space, probability space, with such a convex limit state function, the optimal importance sampling function is going to be the density of the random variables censored in the failure domain. Okay, so actually this is good news. We know how such an optimal importance sampling function looks like. The question is, can we use this function in order to sample, or how feasible it is to use this function in order to sample and estimate the probability of failure? Actually, it's not very practical, not very feasible. This is because it requires knowledge of the location of the failure domain, which we do not have a priori. And it also requires knowledge of the actual probability of failure, which is what we want to estimate. Okay, so we cannot directly use this function. However, because we know how an optimal importance sample density looks like, we can somehow derive suboptimal importance sample densities in order to sample from that they should look as closer as possible to this expression. A typical choice of the importance sample density is to use a Gaussian density that is centered at the form design point, which I denote through this expression here. Okay, x0 in this case is the design point. What is the problem of this choice? This importance sampling function leads to an importance sampling weight function that goes to 0 when n, which is the dimension of the random variable space, goes to infinity. This means that the distribution, because actually the mean of this weight is always 1, okay? However, it goes to 0 for n goes to infinity. When n goes to infinity, we will get a very skewed distribution of these weights. Most of the weights are going to take values at 0, and some weights we're going to take large values in order to compensate and give us an unbiased estimate. Okay? This means that in principle, in practice, this choice of importance sample density will lead to a biased estimate for a finite number of samples. Okay, so this has been discussed in a number of papers. There are other types of things we can do. And in particular, we have a number of simulation methods that have been developed the past years, about 10, 15 years, that aim at maintaining this independency on the random dimension of the Monte Carlo method, but reducing its variance. Some of these methods are line sampling method, subset simulation, asymptotic sampling, sequential importance sampling, and cross-entropy-based importance sampling. Today I will focus on a subcategory of these methods, which I call sequential sampling approaches. These methods, they have something in common. They all sample a sequence of distributions that gradually try to approximate a desired distribution. In this particular case, the optimal importance sample density. These methods have been originally, most of them, developed in the statistical community for Bayesian analysis or in the statistical physics community. And some of them, they are called, some of these methods from this community are listed here. When we look at reliability analysis, sequential sampling approaches are subset simulation, sequential importance sampling, which actually, in principle, they are the same method, so with some specific difference, but they are based on the same concept, and the cross-entropy method. So today I will focus on these first two methods, subset simulation, sequential importance sampling. I don't have time to discuss everything, and I think that Ziggy is going to discuss about the cross-entropy method later on today. Okay, so I will first start with sequential importance sampling, and I will describe this in a general way, such that both the subset simulation and, let's say, a different version of this approach can be viewed as special cases of the sequential importance sampling. So we consider a sequence of distributions, which we call Hj from j equals 1 to m, such that okay, there's a mistake here. Here it should be H1. So the first distribution in the sequence is the density of the random variables. And the last distribution of the sequence is the optimal importance sample density. Each distribution is known up to some normalizing constant, Pj. What these methods do is that they sample sequentially each distribution Hj and estimate the corresponding normalizing constants. Okay? So I will describe how these two things are done, how the sampling is performed from the distribution sequence, and how the normalizing constants are evaluated. I will start with the second component, so the estimation of the normalizing constant. If you take the normalizing constant Pj, you can write it as the integral of the unnormalized density, which equals, if you multiply and divide with the previous density in the sequence, this expression over here. This ratio here is the likelihood ratio between the two consecutive distributions, and it's in principle again an importance weight factor. So through this expression here, we can write the ratio of two consecutive normalizing constants as the expectation based on the previous distribution in the sequence of these weights. Okay? And this is how we estimate the normalizing constant. In principle, what we do is that we estimate the normalizing constant of the next distribution by performing importance sampling with the previous distribution in the sequence. Ensuring that these distributions are not that, let's say, different from one another, you are able to ensure this in an adaptive way usually. You can make sure that the estimate of this ratio of normalizing constants is a good estimate. Okay? Okay, so this is how we estimate the normalizing constant. Now, how do we sample from the sequence of distribution? So we are assuming that we have samples from the previous distribution in the sequence, so assuming that we have samples of xk from distribution hj minus 1, then these samples are also weighted samples when we pair them with these weights of the next distribution in the sequence. These weights here are in principle the likelihood ratio between the two subsequent unnormalized densities. Okay? So already by having samples from the previous distribution, we get weighted samples from the next distribution in the sequence. What we do is that we perform a resample move scheme. In the first step, in the resample step, we start from the weighted samples to get uniformly weighted samples or unweighted samples from the distribution Hj. Okay, this we can do by any random sampling technique. And at the second step, in order to increase, let's say, decrease the correlation between the samples, we perform a move step. We move the samples, apply an MCMC, Markov chain Monte Carlo, with invariant distribution, the distribution Hj. Okay? So this is how it's done, resample, and then move with MCMC. Okay, so this is basically how this method works. Now, let's look at how to choose these distribution sequences. One possible choice is to choose the sequences choose the sequence as by using the optimal important sampling densities from a sequence of reliability problems with nested failure domains. Okay, so if you look at this sequence here, this is the optimal important sampling density from problem with failure domain Fj, such that, and Fj are defined such that the sequence is a nested sequence. Okay, this can be done by, for example, defining these failure domains as limit state function smaller equal than some constant c, where this constant c in the first step is infinity and in the last step is 0, and we have some values in between. This is, for example, how such a nested sequence of failure events might look like. This is the first failure event, and this is the last failure event. Okay? So this particular sequence leads to the subset simulation method. So this is kind of an unconventional way to present the subset simulation method. But actually, if you apply what I have discussed so far with this particular sequence, you end up with exactly the same method. Okay, as most of you, I guess, are familiar with. What is the particular, let's say, consequence of using this distribution sequence? Actually, when you go and evaluate these weights, okay, these weights when you try to, you want to obtain, to perform the resample move scheme, to sample the next distribution, you will get weights of 1 if the samples lie on the next failure domain and 0 else. So if you sample 1,000 samples, for example, and you will get weights of 1 only if your samples lie on the next failure domain and 0 else. So you will get only a fraction of your samples that you can use in order to perform the move scheme. Okay, let me try to illustrate this a little bit with an example. We start from our distribution, from samples from the distribution of the random variables. Okay, this is the final failure domain. This is the first intermediate failure domain. So if you basically take the ratio between this density censored here and the density censored here, these samples are going to get weight 1 and all these other samples are going to get weight 0. So when you actually go and resample and move to and obtain samples on the next failure domain, you will just get all these samples here, so one fraction of the samples, which will have weight 1. This means that your samples already directly follow the distribution that you want to simulate with MCMC. And this is why, actually, when you apply the MCMC to move the samples, you don't need to apply any burn-in. So for those of you who are aware of Markov chain Monte Carlo method. Okay, so what we need to do then is to start the chain from each of these samples and generate the samples in the next failure domain. And we continue the same way until we reach samples that follow the optimal important sampling density. Okay? This is how the method more or less works. So as it should already be clear, the method, for the performance of the method, the crucial ingredient is to use an efficient MCMC sampler. The reason is that you have only a small fraction of the samples that you can move, and then you need to apply a chain, Markov chain from this sample, which has length greater than 1. So actually having an efficient sampler, which results in low correlation, is very beneficial for the quality of the samples and therefore for the quality of the probability estimate. So MCMC sampling is a method that generates states of a Markov chain that follow some target distribution. Okay? A standard algorithm for performing this is the Metropolis-Hastings algorithm. The Metropolis-Hastings algorithm for sampling from this target distribution in the particular case, it looks like this. You perform its transition from this transition density, which consists of two components. one component says that I move my samples with some proposal density Q, and the other component says that I will actually reject these samples with probability 1 minus A, where A is basically or alpha is the acceptance probability of my chain. Okay. The acceptance probability looks like this for standard metropolis hastings, where Q is the proposal distribution. In this case, F is the density of the random variables, and I is the indicator function. Okay. In the standard random walk sampler, we can use as proposal density the Gaussian density centered at the current state of the chain. Okay. The acceptance probability in this case, because this density is symmetric, reduces to this expression here. This expression is governed by this ratio of the standard normal, or the density of the random variables at the current over at the candidate over the current state. It has been shown that this ratio actually takes very, very small values as the dimension of the random variable space increases, especially in the case where we are dealing with independent densities. Okay? This can be illustrated by this. And this will actually lead to this acceptance probability take very, very small values in high dimensions. This is illustrated on this figure, where you see the average acceptance probability or acceptance rate for different number of random variables, for sampling Gaussian target distribution, and for starting at different locations away from the origin. Okay, you see that for all these curves, the acceptance probability decreases very fast with increase of dimension, such that when we reach around 20 dimensions, almost all the samples are going to be rejected. Okay, this will lead to extremely high correlation between the samples, and will undermine the quality of the probability estimate. Okay, this has been again discussed in several references. So there is a couple of ways to deal with this issue. There's two algorithms that I believe work more or less equivalently well. One is the component-wise or single component metropolis algorithm, which is the algorithm that was originally proposed for use within substance simulation. And the other one is the conditional sampling algorithm, which is, let's say, an algorithm that works particularly well in high dimension and has a much simpler implementation than the single component metropolis hastings algorithm. I will shortly discuss this algorithm. In this algorithm, actually, it's very simple. What you need to do is choose as proposal distribution a multivariate Gaussian conditional on the current state of the chain. If your distribution of the random variables is Gaussian, which is typically the case for the reliability problems we're working on, even if it's not the case, we can go and transform to what we call an equivalent Gaussian space. Then the acceptance rate equals the indicator function. What does this mean? That actually this whole thing here vanishes, and we only end up with the indicator function. So if we sample from this proposal, we will accept all samples that fall in the failure domain and reject the rest. Okay? This means that because this ratio of densities disappeared, the efficiency of this algorithm is actually independent of the dimension of the problem. Okay? In addition, we have looked at optimizing the performance of this algorithm by choosing adaptively the correlation parameter between the current and candidate state of the chain. We have seen that the performance of the algorithm becomes optimal when the acceptance rate of the algorithm is around 44%. So we have derived an adaptive algorithm that chooses the correlation parameter adaptively, such that it steers the acceptance rate to come close to 0.44. Let me show an example on this. This is a one-dimensional diffusion problem. So it's a very standard problem that, for example, could be used to model the static equilibrium of a bar. The log diffusivity in this problem is modeled by a Gaussian random field, which is a certain autocorrelation function, and it is discretized by Cornell-Levy expansion, which leads to 200 random variables. So it's a pretty high-dimensional problem. The spatial domain, in this case, is discretized by 100 piecewise linear finite elements, and the limit state function restricts the value of the unknown function at the end of the domain. What you see here is the coefficient of variation of the probability estimate with decreasing value of the failure probability. So here we have 10 to the power of -7, here 10 to the power of -2. Okay, so as we know that this coefficient of variation should decrease more or less linearly with the logarithm of the failure probability when we apply subset simulation. I compare here the performance of the conditional sampling algorithm, the component-wise Metropolis-Hastings, with their standard settings, together with the adaptive conditional sampling algorithm that kind of steers the value of the correlation parameters to achieve the optimal acceptance rate. You see that the coefficient of variation actually in this case can become considerably lower when we use this adaptive approach, especially as the probability of failure decreases further. This, I have to say, is done with no additional computations of the model. So it's basically done on the fly. Okay. Okay. So that was my short discussion on subset simulation and on the efficiency, on its efficiency at high dimensions. I'll shortly discuss another choice of the distribution sequence. So I have again here the optimal importance sample density. So before, what we did, we used the optimal importance sampling densities for a sequence of nested failure domains. Instead of this, we can take this expression and substitute the indicator function with a smooth approximation of this function. Okay, so this basically is a smooth approximation of the indicator function. The parameter sigma is a positive parameter that controls the smoothing of the indicator. This is how a sequence of such a sequence might look in one dimension. We start with the density of the random variables, and slowly we reach the density that is close to the optimal importance sample density through subsequent smoothings of the indicator function. Okay, so unlike subset simulation, we have here a smooth transition from the density of the random variables to the optimal importance sample density. What does this mean? It means that actually when we go and evaluate these weights, the weights are not going to be equal to 0. So all of these weights will take some value that is different than 0. Okay? This has the implication that actually to converge, when we apply MCMC on the second step, to converge to the stationary distribution, we might need to apply a short Berninian period, which is not needed for subset simulation. So for applying MCMC algorithms for this sequence of densities, there are two possibilities. One possibility is to apply this conditional sampling algorithm that I presented before. It actually works the same way as with subset simulation, and it leads to dimensionally independent performance. And another possibility is to use an independent Metropolis-Hastings algorithm, which works quite well for low to moderate dimensional component and system reliability problems. This idea is based on using these weighted samples, okay, that we get, which is basically the same. They have the same number as the total number of samples, so we get a large number of weighted samples in order to fit a distribution model. Okay, this distribution model is then used as proposal density in the MCMC algorithm. One possible model could be the Gaussian mixture model. So how this method works is that we start with, again, the samples from the density of the random variables, and then we apply weights in these samples. Okay? So these samples that are closer to the failure domain will have higher weights than the samples further away from the failure domain. Then we resample and move these samples by using MCMC, and we get something like this. In order to apply the independent metropolis hastings, we could directly use these weighted samples in order to fit the Gaussian mixture model and apply this as proposal density in order to perform the move step. Then we weigh again these samples, resample, move, and so on until we get samples that are close to the optimal samples from the optimal importance sample density. One example on this, I'm showing here a series system reliability problem with 4 components. This is the optimal importance sampling function, and these are the samples I get in the final sampling step of this method. Here I'm comparing the performance of subset simulation with the performance of the sequential importance sampling method with smooth transitions, and I'm checking 2 different number of terms in the Gaussian mixture that I used as proposal density in the independent metropolis hastings. What you see is that for this problem, SIS performs better than subset simulation in terms of coefficient of variation. So if you compare this column here with this column here, so every row corresponds to a different number of samples per level. While, okay, subset simulation is unbiased from the independent of the number of, or already for 500 samples per level, while for the sequential importance sampling, the unbiasedness comes as we increase the number of samples. This has to do with the fact that in this simulation, I didn't apply any burn-in my MCMC move. Okay, as my samples increase, then I get a better, let's say, approximation of my target distribution from my proposal density, and I get already an unbiased estimate even though I don't apply burn-in. Okay. Now, as I increase the number of terms in the Gaussian, my results become worse in this case. Actually, in this case, I already know that 4 terms in the Gaussian should be good enough because I have 4 components in my series system problem. So as I increase the number of Gaussians, I have a larger number of terms to fit in my proposal density. So my quality of my fit becomes worse. So therefore, the results with 10 terms in the mixture are worse than with 4. I also saw a comparison of this method for high-dimensional problems. So this is a very standard problem, which is a linear function of standard normal random variables whose probability of failure does not depend on the number of random variables. In this case, I choose the beta parameter as 3.5, which results in a probability of failure of 2 times 10 to the power of minus 4. This is what I'm comparing is the conditional sampling algorithm with the independent metropolis hastings algorithm in terms of bias and coefficient of variation. What you can see here is that the conditional sampling algorithm has independent performance on the number of random variables, while the Gaussian mixture performs actually better than the conditional sampling in low dimensions. But after we reach dimensions of 20, the performance of this method becomes worse. Okay, so based on this, we can use the Gaussian density or the Gaussian mixture proposal for sampling low dimensional problems, and as we go to higher dimensional problems, we have to switch to the conditional sampling algorithm. If I compare subset simulation with sequential importance sampling with conditional sampling algorithm, I see that, first of all, the performance is independent on the number of random variables. However, the mean estimate in both cases is unbiased, and the coefficient of variation of the subset simulation is smaller than the one for sequential importance sampling. This actually tells me that if I want to work with really high dimensional problems, subset simulation is the better choice. Okay, so let me make some observations on these 2 methods. The subset simulation allows using only a fraction of the samples from its previous distribution in the sequence, okay, because only just a fraction of the samples takes weight of 1, all the others take weight of 0. Therefore, the Markov MCMC within subset simulation does not require burn-in. And we saw that efficient MCMC algorithms allow application to very high-dimensional problems. I have to say that many times subset simulation is regarded as a method that works very well in high dimensions. One should always keep in mind that this has to be paired with the appropriate MCMC algorithm. If you don't use a good MCMC algorithm, the method will fail in high dimensions. Now, when we look at SIS with smooth transitions, this allows using all the weighted samples from its previous distribution in the sequence to fit optimal MCMC proposals. And this leads to optimal performance in low to moderate dimensional problems. Some problems of both approaches that I want to mention is that we have no reliable estimate of the accuracy of the probability estimate in both cases. So there are estimates, but they're not that reliable. And the probability estimate becomes rather skewed with decrease of the target failure probability. This has to do with the fact that we, in the end, compute something as a product of estimates. So as we increase the number of estimates in the product because of the central limit theorem, this is going to converge to a log normal distribution, which is positively skewed. This means that we more often are going to underestimate than overestimate the failure probability. Okay, I just have a very short excursion on approaches for reducing computational cost. So I'm not going to discuss details here. There is a presentation coming after me that is going to discuss such approaches in detail. So one can use surrogate models in order to make things faster. In particular, one could use adaptive surrogate models and couple them with these type of sequential sampling approaches. One can use samples in each intermediate density in order to, from each intermediate density in order to get a better fit of the surrogate model. In this paper, we used artificial neural networks, but there are also other types of surrogate models that can be used, as Bruno will discuss in the next presentation. I want to shortly discuss one category of methods that is not that, let's say, popular in our community. These are multi-level methods. Multi-level methods or multi-fidelity methods, they define a sequence of models. This sequence of models is of increased fidelity in a sense, or increased accuracy, but also increase in computational cost. So it tries to kind of shift most of the computations in the cheaper models, but more inaccurate than the more accurate models. This is one attempt that we try to define a multi-level method that is based on subset simulation. And you see the computational cost, which actually decreases with increase of the number of levels, or with decrease of the target failure probability. So as the target failure probability decreases, we can gain much more computational cost, and this is in particular in three-dimensional applications or models. Finally, I just want to make a very short note on Bayesian analysis. These sequential approaches for reliability analysis can also be used in order to perform Bayesian analysis, in order to learn distributions of random variables, and to update failure probabilities. And this is enabled by equivalent definition of the Bayesian updating problem through an equivalent structure reliability problem. Therefore, all these methods that I have discussed until now can also be used for solving Bayesian updating problems. Okay, then this brings me to the end of my presentation. I want to summarize. I discussed sequential sampling approaches for reliability analysis, and I focused in high dimensions, mostly. These methods are based on sampling from a sequence of distribution that gradually approach a target sampling density. Sequential importance sampling with smooth transition performs well in low to medium dimensional problems. And subset simulation, in my opinion, remains the optimal choice for high dimensions, really high dimensions. And with this, I would like to thank you for your attention.